Hello, everyone. Welcome to my presentation. My name is Renchi, and I am a research fellow at NUS. Next, I will introduce our work, scaling attributed network embedding to massive graphs. First, let's define the problem we studied. Given an attributed graph where each node has associations with some attributes, such as gender, age, or a user in an online shopping website, the objective of attributed network embedding is to map nodes to low-dimensional embedding vectors, which can then be used as input to downstream machine learning tasks. For example, we can use the embeddings as features and then train a classifier based on the embeddings for node classification tasks, including user tagging in social networks and fraud detection in financial networks. As another example, we can take the embeddings of two different nodes and use a classifier to decide whether the two nodes are likely to be connected in the future. This approach is adopted by Pinterest to recommend images and videos to users, and by Alibaba to recommend products to customers. Many of the existing solutions for attributed network embedding are based on expensive learning techniques, such as autoencoders. This leads to significant computation costs and makes it difficult to handle large graphs with billions of edges. Meanwhile, there exist some other methods that are more efficient, but the embeddings that they generate are not as good. To remedy the deficiency of the existing solutions, we propose a new method named PANE for attributed network embedding. PANE significantly improves our existing solutions in terms of computation efficiency without compromising the embedding quality. Our solution is based on the following idea. First, we formulate attributed network embedding as a new matrix factorization problem. Second, we solve the problem efficiently using SVD and coordinate descent with non-trivial space and time guarantees. Our experiments demonstrate that PANE is orders of magnitude faster than existing solutions, while achieving better results for node classification and link prediction. In addition, PANE is also able to handle billion-edge graphs using a single server. More specifically, the matrices that we factorize in our solution are matrices that store some affinity measurements between nodes and attributes in the input graph. Our affinity measurements are obtained using a new type of random walks. In the following, we will first introduce our random walks and our affinity measure, and then explain how we construct our affinity matrices and factorize them to obtain our embeddings. Let me first explain the random walks that we use. Given a source node U, a node to attribute random walk starts from U and jumps to an out neighbor of the current node or stops with alpha probability at the current node. Once it has stopped, it picks an attribute R of the current node according to the weight of the node attribute association. The intuition here is that the random walk samples an attribute R from the neighborhood of node U. If R appears frequently in the neighborhood of U, then it has a higher probability to be sampled. Intuitively, such an attribute R has a strong relationship with U. Based on the above notion of random walks, we define the node attribute affinity FUR between node U and attribute R as the normalized probability of this node to attribute random walks. In addition to the random walk that goes from a node to an attribute, we also define a type of random walk that goes from an attribute to a node, and we'll explain why we do this. The attribute to node random walk from an attribute R first picks a node S having attribute R according to the weight of their association, and then starts a random walk from S until terminating at a node V. The intuition here is that if a node V has a strong connection to an attribute R, then the random walk from R has a relatively high probability to sample V. Based on this notion of random walks, we define the attribute node affinity BRV between node V and attribute R as the normalized probability that an attribute to node random walk from attribute R ending at node V. So why do we define a node attribute affinity as well as an attribute node affinity? The reason is that we can combine these two affinities to implicitly model the affinity between nodes. Intuitively, if we have a random walk that goes from a node U to an attribute R, and we have another random walk that goes from R to another node V, then the combination of these two random walks can be regarded as a random walk from U to V with a teleport in the middle. Based on this intuition, we define a node-node affinity measure as follows. The node-node affinity PUV between node U and node V is the summation of FUR times BRV over all possible attribute R, where FUR is the node attribute affinity and BRV is the attribute node affinity. The advantage of this indirect approach is that we only need to construct matrices to store the node attribute affinities and the attribute node affinities, and then each matrix takes big OND space, where N is the number of nodes and D is the number of attributes. In contrast, if we directly construct a matrix to store the node-node affinities, then it takes big ON square space. Now, the question is, how can we construct embeddings to capture the affinity measurements that we just mentioned? The idea is as follows. We aim to construct a forward embedding matrix XF and a backward embedding matrix XB for nodes, and an embedding matrix Y for attributes, such that XF and Y can reconstruct node attribute affinities, XB and Y can capture attribute node affinities. Let N be the number of nodes, D be the number of attributes, M be the number of edges. The construction of the two affinity matrices takes only big OND space and big OMD time. Then we jointly factorize F and B to obtain the embedding matrices. We formulate the joint factorization of F and B as a least square problem. This problem can be solved using coordinate descent, but the algorithm may need a large number of iterations. Fortunately, we find that it is possible to obtain a good initial solution to the problem using SVD. From this initial solution, we only need a small number of iterations to get high-quality embeddings. Furthermore, the algorithm can be parallelized to achieve even higher efficiency. The overall time complexity of our algorithm is big O MDT plus NDKT time, where M is the number of edges, N is the number of nodes, D is the number of attributes, K is the embedding dimensionality, and T is the number of iterations. In our experiments, we used 8 datasets with up to 50 million nodes and almost 1 billion edges. We compare our proposed PANE method against 6 neural network-based methods, 3 matrix factorization-based methods, and 1 other method. We set the embedding dimensionality to 128, which is a common setting in the literature. Here are the results for the node classification tasks performed using the embeddings generated by each method. The x-axis of these figures represent the percentages of nodes used for training. The y-axis represents the F1 scores. Overall, the F1 score of our solution is higher than the state-of-the-art by 3.4% to 17.2%. Here are the results for the link prediction tasks. The table here shows the performance of each method for link prediction, measured by the area under the curve, or AUC for short. The AUC of our solution is 0.9% to 6.6%, higher than the state-of-the-art in almost all cases. The only exception is on the Google Plus dataset, where our solution is outperformed by a competing method by a very small margin. In the next set of experiments, we measure the running time of each method on all data sets. The y-axis here represents the running time in log scale. In general, our solution is orders of magnitude faster than competing methods. Even on this largest data set with close to 1 billion edges, our solution can terminate within 12 hours using 10 threads. That's all. Thanks.